Right, hello. Now, I've just come out the shower, feeling relaxed. Could sit down and watch a bit of telly. Think Room 101's on. But no, yes, this is another revision video. We're doing a bit of physics today. We're doing from the AQA A2 syllabus of physics. And by the way, we've had a few letters in. They've been through the roof, actually. There's been loads. And, I don't know whether I've changed my hairstyle or anything, but look at this saucy letter, eh? Look at that. Oh. Tomato ketchup. Right, that's pun of the day. Now, hello. Now we're going to be doing probably the most awkward bit to revise in the whole course of physics, in the sense that it's not actually in the textbook. Yes, it's the optional unit. Now, you can take 1 out of 4 options: astrophysics, medical physics, applied physics, or what we're doing, turning points in physics. Those key discoveries which led us to believe and apply all the physical laws that we know today. Lovely. Now, there are 3 parts to this unit. There's discovery of the electron, which is what we're going to be doing today, and then there's wave-particle duality and special relativity. But we won't talk about them today. We're going to be talking about the discovery of the electron. One of the most important discoveries of all time, probably, seeing as though... Oh my god, I'm terribly sorry. Right, what was that? Yeah, one of the most important discoveries, because the electron basically explains the laws of chemistry, pretty much, in a nutshell, let's be honest. And it explains what things made of, what we're made of. It gave us an idea on what the actual atom was. We had a bit of an idea what the atom looked like, but we didn't know really how charge was distributed at this point. What the universe is made of. So there's the inspirational statement to start off the topic. Let's get into the nitty-gritty, shall we? Now, the thing that really got the scientists thinking was cathode rays. God, yeah, it was cathode rays, yeah? Now, cathode rays, we know now, are made up of beams of electrons. They didn't know that then, which is what they wanted to find out. So let's have an insight on what a cathode ray actually is. What happens is something called firm ionic emission. Sounds like a big 2 words, that. It's quite easy once I explain what firm ionic emission actually is. So what you've got to remember, in a metal, there are loads of delocalized electrons which aren't joined to any atoms at all. They're moving about all over the shop. Now, give those electrons enough energy, and they'll have enough energy to leave the metal completely. Swoom, right? So, what a cathode ray consists of is a coil of wire, lovely coil of wire. If we connect that to a power supply, AC power supply, I don't know, right? What you'll get is a lot of resistance in the wire. That'll cause the wire to heat up. And as you heat up, you give those atoms more energy. They're bumping about all over the place. Boom, boom, boom. Now, those electrons will be moving about all over the place as well. And some of those electrons will have enough energy, they'll have enough kinetic energy to leave that coil of wire completely. Whoom! Right? Out there. Now, that's why it's called thermionic emission, because it's being heated, thermal, ionic, because we're losing charge, remember what ions are, and emission, because they're leaving. Now, once the electrons are left, we will apply an electric field. What we do, we're going to place 2 plates, and the anode is going to be here. Remember, the anode is positive. Now, we knew, in the 1800s, these scientists knew that these electrons were negatively charged, and then they had momentum, mass, and energy. So they knew all that. So they knew if we put an anode here, the electron, being negatively charged, will be attracted to the anode. So therefore we've constructed an electric field here. Let me just make sure I'm doing this right. Yes, lovely. So, what you can do is make a little hole in the anode. Some electrons will be attracted to the anode, but some... well, they'll be attracted, all of them will be attracted to the anode, but some will pass through the hole in the anode. So this electric field will accelerate these electrons So when they leave through the hole in the metal anode, they'll leave a constant motion. They'll carry on travelling in constant motion because once they've left the anode, there are no forces acting on it. This electron is now in uniform motion. So we have a beam, a thin beam, because the hole in the anode is quite small, thin beam of negatively charged particles. Now the energy, the kinetic energy on these electrons is given by half mv squared equals EV. Now, let me take you through what this means. Half mv squared is the kinetic energy. You should know that formula. EV, what do these mean? E is the charge on an electron, which they didn't know back then, remember? And V is the voltage applied. Does that make sense? Let's remember our definition for the volt again, shall we? V equals the work done per unit charge. V equals W over Q. So the work done is going to be, if we do a bit of rearranging, V times Q. So that energy there is going to equal the kinetic energy because there's no other forces. So the energy exerted by this electric field is the only energy which is the only form of energy which these electrons can get. Because after that, they're just travelling in uniform motion. Now, one of the things that was discovered before the actual charge of the electron was the E over M ratio. What's the E over M ratio? E stands for the electric charge of an electron over the mass. So it's the charge over mass, the specific charge, if you like. How many charge there is per unit mass. Now, believe it or not, that was known before the actual charge on the electron was known. Now, these experiments were all done by J.J. Thomson, I think. Hang on, let me just... it probably was. Let's go with that. You'll be able to tell in the comment section below whether I was right there or not. Now, the way in which we were able to find out the charge to mass ratio was using another tube. What we got was a cathode ray tube, like this, I think. So that will produce your electron beam. I'm right on this, by the way. I just have to keep checking back to the book, just in case I mess up your education. Yeah, okay. So what you've got a beam of electrons. Now, instead of your normal cathode ray tube, we're going to exert a uniform magnetic field. I could draw this, but I can't draw, so I'm not. Now, if you remember from Unit 4 of physics, you'll know, if you know the motion of the current, the charge, so in this case on the electrons, and you know the way, the direction of the field, you'll be able to work out the motion of your electrons. And what you'll find out, if the magnetic field is always at right angles to the motion of the current, the direction of the current, then what you'll end up is the electrons will just carry on moving in a circle, a uniform circle. Details on why that is on Unit 4, so we don't need to worry about that for the moment. So what you can say is that these electrons are now in uniform circular motion. And that means we can apply some of the formulas we learned in Unit 4 from circular motion. mv squared over r, that's still relevant, mv squared over r is the force. We also know another equation for force. In an electric field, a charged particle in an electric field is equal to F equals BeV. If it's an electron in an electric field. Let's go through what these letters mean. In mv squared over r, m is the mass of your electron. V is the velocity that the electron is moving at, and r is the radius of the circle, right, which we can measure. Something I should have mentioned is that when we fire these electrons, it's in a container of gas, which when the electrons pass through it, it excites the atoms in the gas. If you remember from excitation energies in AS, you'll know that electrons will get excited, they'll move to higher energy levels when they absorb the energy, and then they'll move back down emitting light. That light is visible to us, so therefore we can see the path of these electrons. Of course, the electrons are invisible, so we're just seeing the paths that they make. So that's how we detect and know that they're moving in a circle, right? So that way we can work out the radius of a circle. That's easy. What about in this equation here? F equals BeV. B is the magnetic flux density. We can measure that. We know that. E is obviously the charge of an electron, and V is once again your velocity. Now you can combine these two equations, obviously. So mv squared over r equals BeV. And then, let's do that, shall we? And then what you can do is find the E over M ratio. So if you put that on the other side, E over M equals V over BR, I think, if you rearrange that, because the V's cancel. So you've got V over BR. Now, two of those quantities here we can measure. We can measure the magnetic flux density, and we can measure the radius. We can't measure V, however. However, we've got an equation for V here, which we can rearrange. If you do a little bit of mathematical wonderness on that, you'll get E over M equals 2V V squared R squared. Something I've got to make clear is the difference between big V and little v. Big V is voltage. Little v is velocity. Okay, and they come up together here, so you've got to be careful. So you end up with that. If we rearrange that to make V the subject and plug it in wherever you see little v here, you'll get that. So the E over M ratio is equal to 2 times the voltage, which we can measure, over the magnetic flux density squared, we can measure that, and the radius squared. So there we can find the charge over mass ratio of an electron. Now, that didn't help find the charge of an electron, the actual charge of an electron. So a few more experiments are needed because we didn't really know the mass of an electron either. So E over M, I mean, it didn't really help that much. So that's when Robert Millikan came in. What a guy. So Robert Millikan and his oil drop experiment. This is one of the key experiments ever, apparently. I read that somewhere. God knows why I'm on there. Right, Millikan's oil drop experiment found the charge of an electron using tiny little droplets of oil. Now before we do that, we have to understand something called Stokes' law. When something is moving in a fluid, it eventually reaches terminal velocity. Therefore, the force of the object's weight equals the drag force due to resistance. Now we know an object's weight is mg, mass times g, 9.81, on Earth anyway. The drag force is something called Stokes' law. F equals 6 pi eta rv. Now there comes a point when something's moving, mg equals 6 pi eta rv. Now what he did, well, he got some oil and he used an atomizer to spray them into tiny, tiny little droplets, so tiny that they could only be seen using a microscope. And then he'd spray them through this little tiny, fine hole in a plate and allow the drops to move down. As they'd move down, they'd reach terminal velocity, and that was the point. Now, he could just let them fall, but the other thing that was in the experiment were two metal plates. Let me sort of draw you the sort of structure here. Just go over the page here. Right, we have your anode here, and your cathode here. And you've got a little tiny hole in the anode here where these tiny oil droplets can pass through. So when you've got a potential difference added here, something interesting happens. Now, these oil droplets have been charged due to the atomizer. We don't know how many electrons have been moved off them, but they have been ionized. Electrons have been moved off. We don't know how many. That's the whole point. So any charge that we get here won't be the charge on one electron. So these positively charged oil droplets are moving down here. Now when we add a potential difference here, let's zoom in on this a little bit. Here's an oil droplet. It's falling due to its weight, mg. When we add a potential difference, that causes this electron to behave rather differently. It stops moving down as much. That's because there's now an electrical field present. So this gravitational field is fighting with the electrical field. Now, electrons are negatively charged, we know that. So therefore, these electrons are going to be attracted to the anode here, this positively charged particle. So something is pulling, the gravitational force is pulling the oil droplet down, but the electric force from the anode is pulling the oil up. So we've got a bit of a tug of war going on here. Now there comes a point that's at a specific voltage where the oil droplet will just remain in mid-air. Why is that? It's because the electrical force acting upwards equals the gravitational force acting downwards. So they cancel each other out. So what you'll get is an oil droplet suspended in mid-air. Now that's very useful. Right. Then we start plugging numbers into things. How exciting. So we left you at this. mg equals 6 pi eta RV. Something I should have said what these words mean. Eta is a one we don't really know yet. Eta is the viscosity of a fluid, how easy it is to move through. So golden syrup, for example, has a very high viscosity, water a very low viscosity. Now what we can do is substitute some values here. M, we can't measure the mass of an oil droplet, that's impossible, right? So what we're going to have to do is replace that with another value. We know that density, rho, equals m over v, mass over volume. So we know that mass equals rho v. V, we're assuming that these oil droplets are spherical. The volume of a sphere is 4/3 pi r cubed. So what we can do, we can plug that in there. Pi r cubed g equals 6 pi mu r v. Then we can do a bit of jiggery pokery on that, and let me just find the rearranged version for you. You'll get r equals square root of 9 eta v2 over 2 rho g. Right. I'm not going to go through the full derivation of that, but you could probably do it yourself from that, to be honest with you, because I can already see here that the pi's will cancel, and one of the r's will cancel, so you get squared, so that's where the square root comes from, and blah blah blah. Now, this is very important, because we can now know the radius of the oil droplet, which is obviously impossible to measure. You can't measure the radius of a tiny little oil droplet. Impossible. But now we know, because we've got square root of 9, we know that, it's a number. Eta, we know that. That's the viscosity, remember. V velocity, we can know that because we can see the distance it moves in a certain time. So we can use distance over time because it's a terminal velocity, it's not accelerating. 2, that's a number. Rho is a density, which we can work out. We can work out the density of oil quite easily. And G is 9.81, we know that. So that's quite easy. Now what we have to do is combine all these things together. Now, the electric force acting on the oil droplet when the PD is applied is equal to QV over D. Why is that? That's coming from our electric field strength equations from Unit 4. Do you remember that E, which stands for electric field strength, is the same as V over D, and it's also equal to F over Q. So rearrange that, you get VQ over D. Yeah? Brilliant stuff. So then, what we do then is, at the point when these oil droplets are suspended in mid-air, you'll get that mg equals qv over d. Now, we can't find m, so we're going to have to substitute all that in again, aren't we? And what you get is qv over d equals 4/3 pi r cubed rho g. Rearrange all of that and you'll get your charge equal to 4/3 pi r cubed rho g d over v. And that's your final, that's the point where you're at now. That seems very, very complex, I admit. But it's lovely because we know all the numbers in there. 4/3, that's a number, pi is a number, r we can work out using this equation here. That's your two important equations really. Rho we can work out, that's your density. G, 9.81. D is the distance between the plates, I should have mentioned that. And V equals your voltage, which you can read. So therefore, using that, you can work out the charge that each oil droplet that Robert Millikan was using had. And this is the exciting bit, this is the climax, this is the bit that you've all been waiting for, this is the, I don't know. So, what Millikan found out was that the charge on all these oil droplets were all multiples of a certain number. What he found was that they were all multiples of 1.6 times 10 to the minus 19. Exactly that number there. So that shows that this charge is quantized. It goes up in equal amounts. This is the fundamental unit charge of an electron. So an electron can't have something can't have a charge between, let's say, 1.6 and 3.2 times 10 to the minus 19 coulombs. It has to go up in these little jumps of 1.6 times 10 to the 19. And that is how we found the charge of an electron, and how we now know it's 1.6 times 10 to the minus 19 coulombs. Thank you very much. And actually, just to end it, I've got the spec here. Just got rid of the spec. There was a speck on the spec. I'm too funny today. Must be the cocaine. Anyway, I'm joking. I'm joking. I was joking about that. Mum, I'm joking. Right. She's probably dozed off by this point anyway. Right, let me just read. I think we've just basically covered everything in the course. So, that's it for the moment. 24 minutes. For the love of God, I don't blame you if you haven't seen this much. My God, see ya.